So let us study a situation where one body collides with the other stationary body, say something similar to a head-on collision between balls in billiards. Let's also assume that this system is closed and isolated. Then we can say that the net linear momentum of the system is conserved, or m₁v₁ initial is equal to m₁v₁ final. And if the collision is elastic, remember the total kinetic energy is also conserved. Now, since we have two equations at our disposal, we can find the final velocities of each of the objects. So rewriting this equation as m1 into v1 initial minus v1 final is equal to m2v2 final. That is, we bring this term to the left, and this one as m1 into v1 initial minus v1 final into v1 initial plus v1 final is equal to m2v2 final square, where we have knocked off 2 in the denominator and brought this guy to the left. And then finally dividing 2 by 1 and doing some basic algebra, we get v1 final is equal to v1 initial into m1 minus m2 divided by m1 plus m2, and v2 final, that is the velocity of the second mass, will equal v1 initial into 2m1 divided by m1 plus m2. Now, a couple of interesting observations. We can see that v2 final is always positive, which basically means that the stationary body or the target body with mass m2 will always move forward, which makes complete sense. After all, when have you seen anything moving in your direction when you hit it with something? Then we can see that v1 final could be of either sign. And if you observe the formula closely, you will find that m1 will move forward if m1 is greater than m2. Because you see, this then becomes positive, implying forward motion, but rebounds if m1 is less than m2. And you would have figured out why so. That is because this is negative. Let us also look at a few other situations, and I would like you to visualize what really is happening. So situation 1 is, say, mass m1 is equal to m2. Then what we get is v1 final is equal to 0 and v2 final is equal to v1 initial. And this is quite like a situation in billiards where upon a head-on collision of two balls with equal masses, ball 1 stops dead and ball 2 takes off with the initial speed of ball 1. So the conclusion is that in a head-on collision, bodies of equal mass simply exchange velocities. And this would be true even if body 2 was not initially at rest. Situation 2 is where m2 is much larger than m1 and is hit by m1. As an example, a golf ball collides with a large stationary cannonball. Then these equations become v1 final is equal to minus v1 initial, because you see in the numerator, m1 being very small, this is almost equal to minus m2. And in the denominator, again, for the same reason, this is almost equal to m2, and so m2 cancels off. And v2 final equals 2m1 upon m2 times v1 initial, where we have again used the same logic and considered the denominator as m2 only, since m1 is very small. Again, this makes a lot of sense because body 1, that is the golf ball, would simply bounce back along the same path it came, and considering the collision is elastic, its speed remains unchanged. As for the cannonball, it moves forward at a very low speed because you can see this quantity is much less than 1. The next situation is that m1 is a massive body, that is m1 is much greater than m2, collides with the smaller body. That is, now we are making the cannonball roll towards the stationary golf ball. In that case, these velocities reduce to v1 final is approximately equal to v1 initial, and v2 final is approximately equal to twice the speed of mass 1, that is v1 initial. Basically, this equation tells us that the cannonball simply keeps rolling on, hardly slowed by the collision, and body 2, that is your golf ball, moves ahead at double the speed of the cannonball. Now, let us take a situation where you have a moving target. That is, both the bodies are moving. So for this situation, the conservation of linear momentum equation would be this. That is m₁v₁ initial plus m₂v₂ initial is equal to m₁v₁ final plus m₂v₂ final. And the equation for the conservation of kinetic energy can be written the usual way as this. So we can solve these simultaneous equations for v1 final and v2 final by rewriting one like this, that is m1 into v1 initial minus v1 final is equal to minus m2 into v2 initial minus v2 final, and 2 as this. Then if you divide this by this and do a bit of simple algebra, what you get is v1 final is equal to m1 minus m2 upon m1 plus m2 into v1 initial plus 2m2 upon m1 plus m2 into v2 initial, and v2 final is equal to 2m1 upon m1 plus m2 into v1 initial plus m2 minus m1 upon m1 plus m2 into v2 initial. Now, an interesting thing to note is that if we make v2 initial is equal to 0, that is body 2 becomes a stationary target, a situation we just discussed, then we get back the equations we derived earlier, that is this and this. So now we will move on to the study of collision in 2 dimensions, which is actually a lot easier than you might think. So in case of a collision on a flat plane where the collision is such that the bodies end up traveling along axes that are different, momentum is still conserved. Quite like this one where the ball was first moving along the x-axis and then the two moved in directions that were along very different axes. So the high-level equation around conservation of momentum still holds true. That is P1 initial plus P2 initial is equal to P1 final plus P2 final. And if the collision is elastic, the total kinetic energy is also conserved. But in 2-dimensional motion, what is often more useful is the component analysis of this equation, that is, writing it in terms of x and y components. So let us do that, and we see along the x-axis, m₁v₁ initial was the initial momentum with the momentum of m2 being 0 since it is stationary, and this should equal m₁v₁ final cos theta 1, that is, we have taken the component of momentum of mass m1 along the x-axis plus m2v2 final cos theta 2 for mass m2 again along the x-axis. Likewise, along the y-axis we can write initial momentum is 0 since we can see m1's velocity is along the x-axis only, and this should equal minus m₁v₁ final sine theta 1 for m1, and we've taken the minus sign with the assumption that all vectors pointing down are negative and up are positive. So for mass m2 we get m₂v₂ final sine theta 2 that has been taken as positive. Well, we can also write the kinetic energy equations, which would be really simple since energy is not a vector but a scalar, and what we get is half m₁v₁ initial square is equal to half m₁v₁ final square plus half m₂v₂ final square. So if you count the number of variables, you will find they are 7, and if 4 of them are known, then we can use these 3 equations to find the balanced 3 variables as well. So I would suggest that you head over to this playlist that covers a lot of stuff around momentum, impulse and types of collisions to get a well-rounded view of this topic. And if you like this lesson, do give a thumbs up, and I will see you in the next lesson.